The purpose of this video is to compare constant velocity to constant acceleration and answer the question, why do we need a different equation to calculate distance? So to do that, let's imagine a race between a rabbit and our friend Pluto, a tiny miniature poodle. So if the rabbit has a constant velocity of 4 feet per second, then that means after 1 second, the rabbit's going to go 4 meters. And the rabbit's going to cover 4 feet every second. So after another second, the rabbit will have traveled 8 feet, and then 12, and then 16, and then 20. And we can see on our position time graph that that's a nice straight line. And math people will tell us that the slope of the line is how fast the rabbit's going. So 4 feet per second. Now, if Pluto has constant acceleration, that's a little bit different. So Pluto's velocity is going to increase, and if the acceleration is 1 foot per second every second, then after the first second, he'll be going 1 foot per second with speed, but then the speed will increase by 1 every second. So 2, 3, 4, and 5. Now when we come to take a look at how far Pluto goes, that's it's a little bit different, because we want to figure out how far Pluto went over 1 second. Well, it started off not moving at all, and it was only at the end that it was going 1 foot per second. So how do we figure out how far he went? Because the speed was changing the whole time. And the answer is that if we pick a velocity that's halfway in between these two, and multiply that by 1 second, that'll tell us how far Pluto went during that second. So that would be half a meter. He continues to gain speed, so we want to find out how much further he goes in the next second. Then we would pick a velocity that's halfway in between these two, 1.5. So he would go 1.5 feet in the next second. And he goes further every second because he's accelerated. That's how come we need a new distance equation. It's the same thing here. We pick a number that's halfway in between 2 and 3, and I think it's 2.5. And then here we pick a number that's halfway between 3 and 4, and that's 3.5. And so that's how far he goes during the next second. And then finally 4.5. So because Pluto is going faster and faster, it covers more distance with every second. And you can see that the total distance Pluto has traveled, this is sort of a running total. Half a foot plus 1.5 is 2. 2 feet plus 2.5 feet is 4.5. Plus 3.5 is 8. Plus 4.5 is 12.5. So Pluto is not catching the rabbit yet. You can see the shape of this graph. Its slope is increasing. It's getting steeper because of acceleration. Now, if we extended this, it looks like Pluto's eventually going to catch the rabbit. And even if you look at these velocities, after the end of 5 seconds, Pluto's actually going faster than the rabbit. So acceleration definitely wins. It just needs enough time. But to review, here's what we learned. So the equation for motion that everybody walked in the door knowing was that distance equals velocity times time. But now as we're studying acceleration, we recognize that with constant acceleration, velocity changes too. So velocity is equal to acceleration times time. And that because the speed is changing all the time, we can't use that first equation for distance. We have to have a new equation for distance. And that is distance equals 1/2 AT squared. The 1/2 comes because of this averaging phenomenon. Right, so that's how come we have to have a new equation for calculating distance.